Hello and welcome back to the lab. Today on the bench is our first candidate for doing an alignment with a function generator. This time we're going to tackle the vertical section of a scope. I have another 7A18 plug-in on the bench. This one actually has a little bit of a interesting modification to it, as this is an option 6 unit. It has an additional switch position over here, which we'll talk about later. So just on a first inspection, a lot of these controls are very stiff. This has not been stored well, so I'm going to have to get in there and get those controls loosened up, freed up. The position controls specifically are almost completely seized. Everything else I think is moving fine. We do have a little bit of impact damage on this B and C connector that we're going to straighten out, get that fixed. But all the normal wear and tear on a plug-in that's this old. So what I'm going to do is I'm going to get the side panels off. I'm going to do the usual switch service on these, just clean up the attenuators, things like that, that we've been through many, many times on the channel. And then we will, once I get all the controls freed up, we'll throw it in the scope, see if it does anything, and if it needs repair at that point, we'll take a look at it and get it repaired and ready to go. After that's all said and done, we'll run it through an alignment and a calibration on one of the function generators. After we get through that alignment and calibration, we'll check it with some accuracies, basic DC accuracy, and some frequency response with the appropriate calibration tools. So we'll see how it goes. I'm really curious to see how well it does. We have we'll start with the 160 megahertz function generator. This is a 75 megahertz plug-in, so we should be able to service it pretty well with the function gen. With that, let me get into servicing the controls, and I'll bring everybody back. Okay, I've got the 7A18 in the 7603, letting everything warm up. And I don't even have the attenuators assembled completely yet. I'm just doing some attenuator checking now, just to see. Okay, I want to run through some quick attenuator checking just to make sure the attenuators are operating what I would consider sanely. There's my trace. Turn off the readout so it stops being noisy. And let's see, we're going to output, I got a 1 kilohertz sine wave at 50 millivolts peak to peak. And we're going to go to DC. And what happened? Okay, so AC works at the moment. Give me some more. It should go down. It does. Keep going. We're at 5 VRMS. Oh, that's why my DC is not working, because there is a DC offset on the waveform. Hey, look, DC works now. as I move the DC offset. There was 100 millivolts DC offset on the wave. That's why it wasn't showing up in the DC settings. So DC is now working, which is good. Go back to amplitude. Let's do 500 millivolts. And we're there. Oh yeah, that attenuator's nice. Two millivolts. You can see the function generator is really struggling down at the low end, which is fine. I mean, I'm asking it for a 7 millivolt peak-to-peak signal. It's not a RF. This is a function generator, not an RF signal generator that I would use for a radio alignment. That's another piece of equipment in the lab. So channel 1 looks good. Let's check channel 2. And we're triggering on channel 2, so that's good. Let's come up. That's what I was afraid of. Little bit of noise on channel 2 and the 1 volt range, so we're going to have to work on that. 5's fine. That's not the function generator. That's the attenuator. So, okay. That's just what I wanted to check before we got into the alignments. So we had a little bit more work to do on this attenuator. And of course we have problems, which is normal for something of this age. I've got the attenuator opened up. This switch is metering okay. This switch is metering okay. This switch is metering okay. And this switch is buzzing out okay for continuity. However, between this point and this point, I have a break in continuity, which means I have a problem with the finger switches on the bottom side of this attenuator. And I need to go digging. I'm going to have to strip off the back side of this, get the barrel out, and then work on adjusting the back side of this attenuator. I'm going to look at what the construction is on this, see what the best way to extract this might be. These usually are kind of a pain in the butt, getting these attenuators out, but especially with, I'll have to take this plate off. Actually, I'll have to disconnect both attenuators, it looks like, because the plate's got to come off to get to those bolts, and then I can get in there and remove some things. So I'm going to be digging at this for a while, getting through here. From the back side, nothing works. If I could just take the barrel off, it'd be easy, but this plate has to come off. This is the readout. This comes off, barrel comes out, and then I can service that contact. The only one that's giving me a problem is the 1 volt per division. Okay, according to the meter, when I test from, let's see, let's get a good camera angle here. Oh, don't smush this board in the back, because this is not together yet. I'm just doing some preliminary testing. But now when I check from here to here, I have continuity, which I should, at least for what that front attenuator setting is. So getting those bottom switch contacts adjusted without taking the attenuator out was definitely on the side of maximum sketch. It is. There's no room to work. And this backboard doesn't disconnect very well. The barrel actually doesn't come out. I was able to get it just out of the way enough. Really, this design is you're supposed to take the front BNC off, and then this whole attenuator assembly is supposed to come out, and then you can surface it that way. But this, I guess I did it in hard mode. But we're good. I'm going to put it back together, and we'll throw some square waves in it and see what it looks like. Okay, a quick way to test these plugins. I'm going to leave this burning for a while. It's got a 6 volt peak-to-peak square wave going into it. If I turn this up, we can see we have a square wave. To keep the tube from aging out on the scope, because I want this to run for quite some time to make sure that the plugin's doing okay before I do an alignment on it, I had the trigger set real high on the waveform. So if the waveform collapses again because the attenuator goes bad, it won't trigger. But that lets me turn the tube all the way down so there's no intensity on it, so I don't risk burning in the tube or anything like that. Let this run for hours and it doesn't prematurely age the tube. So all I got to do to know if it's still going is I just need to look for the triggered light, and just as I cruise by the bench every once in a while, I'll take a look at that and make sure we're still happily triggering. If that is the case, then the attenuator's fine. Let this run for a couple hours, 3-4 hours, maybe all night, or for the rest of the evening, and then dive into an alignment. Okay, we have everything warming up on the bench. As you can see, the function generator's on. This is the cable I'm going to be using to give us the best shot. I am using a high quality BNC cable, and we are going to, for the first one, we're going to use the 4000 series function generator. Now, this is a 160 megahertz function gen. This is a 75 megahertz plug-in. So we're pretty well matched on these because the FG is faster. From the testing in the previous video, or that I will link in the description, we found out that the stability and things like that on this function generator is very good. That's really what you're paying for when you buy, quote, calibration equipment. It's not, it's a signal source, but it's a well-characterized, very accurate, very stable signal source. That's where the function generator is going to kind of struggle, and also with a little bit of speed. I'm expecting a little bit of difficulty when we have to do the edge, the high-frequency compensation where I need fast edges. The function generator might be a touch slow. I also have the scope calibration equipment warming up, because after I get done with the alignment on this plug-in, I'm going to hook it up and I'm going to do some basic checks on and compare it to how it would work, or how it looks against the actual calibration plugins. So essentially the basic checks I'm going to do is bandwidth, DC accuracy, and yeah, really bandwidth and DC accuracy is going to be the two big ones, because edge speed will give us bandwidth. So we'll check the step response, we'll check frequency response of the plug-in, and we will also check just the basic DC accuracy. The other place where I think the FG is going to struggle is I'm going to have a hard time validating all of the attenuator positions. For the most part, you want to take measurements on the largest window possible without going to the edges. So when you do say 5 volts per division, you want 25 volts square wave going into the scope, because that'll give you, oh no, yeah, wait, 5, 10, 30 volt square wave, or 25 volt square wave going in to compare the, to get you the largest throw and get the most accurate measurement. With a 5 volt, I think it's a 10 volt peak to peak max. With a 10 volt peak to peak max, I'm going to have 2 divisions of display at 5 volts. So we'll be able to kind of check it, like sanity check it, but for the best accuracy, which is splitting hairs, I freely admit that, the largest, so you want to stretch it out on the display as much as you can, especially for something like step response. So if you're doing a step response and it's like 0.2 divisions, and that's the clearance, if you can speed the time base up and stretch that step response out, you can get a much more accurate graticule measurement of the step response using one of these older analog scopes. But you have to have a time base that's fast enough, and the 7B92A is well matched for the 7904. This is a 500 megahertz frame. But you also need to make sure, like if I put this 7B92A in my 7603, it'll sweep, it'll run just fine, but the frame can only go horizontally so fast before it becomes for a modern term, overclocked, and you lose the linearity, which would also mean the ruler doesn't line up anymore, the ruler being the graticule, so you lose the measurement capability. It'll still display the waveform, everything will work, you just can't take, you can take comparative measurements, you can't take actual measurements. Okay, well, let's get started with the plugin. I'm going to cruise through this alignment. I don't want you all to have to sit through another alignment and calibration video since I've already done one on a 7A18. So I'm just going to cruise through. I'm going to hit the highlights as we're going through after I've done some adjustments. Again, probably step response, gain or DC accuracy, and a few other things. But for the most part, if you need an in-depth look at doing an alignment on a 7A18, there will be a link in the description below for the video where I go through the alignment procedure step by step. Okay, we can see there's a little noise in the signal, but this is a 50 millivolt square wave, 10 millivolts per division on the front plug-in, and channel 2 looks good. Let's do channel 1. And channel 1 looks pretty good as well, although could use a bit of adjustment. And that looks good right there. Okay, I'm into the attenuator compensation in the front end. I've got the test setup is a little different than what the service manual calls for. I've got the function generator in high Z, but I have a 50 ohm termination on the BNC cable, and I have a RC normalizer on the front input of the scope. Everything else is DC coupled, and we are just tuning for best looking square wave. And on to 50 millivolts. Okay, my function generator almost runs out of gas right at about 10 volts. But I think it does say when you're doing the 2 and 5 volts to remove the 50 ohm terminator. Yes. So we can check 1, 2, and 5 volts without the 50 ohms. We're again running into some of the limits of the function generator. It's kind of running out of gas and not able to give me enough drive because it's not driving a high impedance load, it's actually driving a load. So even though the function generator is outputting 10 volts per division, I'm getting a volt through the RC normalizer. And just to prove that that is the case, we have a 10 volt signal coming into the BNC, 5 volts per division, and we have 2 divisions of display. So all the equipment does agree with itself, which is good. Okay, terminating the function generator in pulse mode and setting it to a 5 nanosecond pulse as the fastest it will go. I have done the high frequency compensation. So This is the step response I got out of channel 2, which is really good actually. Let's see, step response out of channel 1. Which is also pretty good. So I'm happy with both of those. Let's speed it up a little bit and see what the step response is on a 1 nanosecond. So here's the step response that I got out of channel 1. We have the function generator on pulse with a 5 nanosecond rise time, which is the fastest this FG will go. Here's step response for channel 1. Here is step response for channel 2. I'm really happy with both of those actually. Both look in really good shape. So this is the waveform I looked at. The trailing edge, I didn't need anything, so I have a real slow trailing edge but a real high pulse time just to not stress out the function generator. But 5 nanoseconds is as fast as it goes. Let's take a look at a 1 nanosecond and see what it looks like on the high-speed gear. All right, here's what the step response is with a 1 nanosecond. As you can see, right on the trailing edge, we have a little bit of overshoot. Not too bad, considering that we weren't using the correct signal to adjust the plug-in. But it could have been way worse. That's not bad. Move up to channel 1. Again, a touch of overshoot, not